Hello guys, this is Alain again, and now we will talk about Norton's Theorem. Now, what is this Norton's Theorem? Now, Norton's Theorem is another method or technique that is used to simplify complicated circuit. So, Norton's Theorem states that it is possible to simplify any linear circuit, no matter how complex, to an equivalent circuit with just a single current source and parallel resistance connected to a load. Now, if we had a complicated circuit, a circuit network which has a lots of resistors in it and a sources, either voltage or current source, we may simplify it. That is what we call a Norton's equivalent circuit, which is a combination of one current source in parallel with a resistance. So the current source is now what we call a Norton's current, and the resistance is what we call the Norton's resistance. Now, how can we apply Norton's Theorem? So, the procedure in applying Norton's Theorem is that first, we're going to divide the circuit into two groups: the load circuit and the complex network. So, the complex network is the one that we're going to simplify. So, after identifying the complex and the load circuit, we're going to remove the complex circuit to the load circuit. So it leads us that the complex circuit is the one that we're going to manipulate and do the calculation, and we're going to reach it to a Norton's equivalent, which has only one current source and a resistance. So after removing the complex circuit or the complex network, we're going to compute the current SC, or the short circuit current. After computing the short circuit current, this short circuit current is the so-called Norton's current, the value of the current or the source current in the Norton's equivalent circuit. So how we're going to take or to compute the Norton's current is simply by replacing or putting a wire on the open circuit portion where the load is connected, and we're going to compute the current that flows through that portion or through that point. The current that flows through that point is now what we will call a current SC, or the short circuit current, and it is the value of the Norton's current. Now, after getting the ISC, we're going to compute the Norton's equivalent resistance, or the R nor. Now, how can we compute it? We can compute it by simply killing the sources present on the complex network, the one that we removed from the original circuit. So remember, if you're going to kill a source, if it is a voltage source, we're going to remove the voltage source and replace it with a wire to make a short circuit. Well, if it's a current source, to kill a current source, we're going to remove the current source and replace it with an open circuit. Then we compute the equivalent resistance, or the total resistance in the circuit. Then after getting the Norton's resistance, so we're going to connect the ISC and the resistance, the Norton's resistance, in parallel. Then connect the circuit to the load circuit. And that's it. You have the Norton's equivalent resistance and the simplified, the Norton equivalent circuit, or the simplified circuit of the complex network. Now, in order to fully understand how to apply Norton's theorem, we're going to use an example. So for an example number 1, so I'm using the example I use in the Thevenin's theorem video. So for those who have not yet seen my Thevenin's, or have not, or don't know how to use Thevenin's, you may click the link below. I attach a link below so that you may view my video about Thevenin's theorem. Now simplify the circuit using Norton's theorem and find the current at 2 ohm resistor. I'm sorry for the wrong spelling. This must be simplify. Simplify the circuit using Norton's theorem and find the current at 2 ohm resistor. So I really emphasize that on this example we're going to use the Norton's theorem. So here is the circuit. So we have a combination of a resistance with a voltage source. Now, the first procedure is to divide the circuit into 2 groups. So we have the complex network and the load. So the load circuit is the 2 ohm resistor at what it says in the problem. So it is the current. We're going to find the current that passes through the 2 ohm resistor. So how can we solve this? So we're going to remove the complex network from the circuit. So we had an open portion in this part. This is the open portion of the circuit where the load is connected. Now after removing the complex network, we're going to put a wire or making a short circuit on the open circuit portion. So in this way we can find the current flowing through the wire or the short circuit portion, and we're going to call the current as ISC, or the short circuit current, which will be the value of our Norton's current. So in order to compute for the ISC, we're going to use mesh analysis. Now for those who don't know what is mesh analysis, you may click the link below so that you can watch my mesh analysis video and to be able to understand how to use mesh analysis. So at I1, so this is the I1 portion. So the I1 is the current passing through the 9-volt voltage source and the 4 ohm resistor and the 6 ohm resistor. So creating the equation, it will be the -9 plus 4I1 plus 4I1 I2 plus 6I1 equal to 0. So simplifying the equation would lead us 14i1 minus 4i2 is equal to 9. And we're going to call it as an equation number 1. So the next thing is we're going to get I2, or the loop I2, which is the current that flows through the two resistor, namely the 4 ohm resistor and the 5 ohm resistor. So the equation goes 4 times I1 minus I2 plus 5I2 equal to 0, since there is no sources present on this loop. Simplifying the loop will lead us negative 4I1 plus 9I2 equal to 0. Then we're going to simplify more to get one of the equation. So it shows that I1 is equal to 9 over 4I2, and we're going to call it equation number 2. Now from this, we're going to substitute equation 2 to the equation 1. So it shows that 14 times 9 over 4i2 minus 4i2 is equal to 9. And further simplifying the equation, or computing the equation, will lead us that I2 is equal to 30.3273 amp. So since I2 is the one or equivalent to ISC, so automatically the value of the ISC is 0.3273 amp. Now we're going to compute the Norton's equivalent resistance. Now to compute the Norton's equivalent resistance, we need to kill the sources. So in this circuit, the only source present on the circuit is the voltage source. So we're going to remove the voltage source and replace it with a wire to make a short circuit. Then we'll compute the total resistance as seen at this portion, or at the open circuit portion. So therefore, the Norton's equivalent resistance is equal to the series. This is the series resistance of 4 and 6 in parallel with another 4 ohms, then in series with the 5 ohm resistor. So substituting the value and computing the value will lead us that the Norton equivalent resistance is 7.71 ohm. So there you go, we have the Norton's equivalent resistance. So after getting the Norton's equivalent resistance, we're going to combine the two, the Norton's current and the Norton's resistance, wherein the Norton's current is the short circuit current that we have solved previously. And now we're going to get the current at 2 ohm resistor. So to get the current at 2 ohm resistor, we may use a mesh analysis or a nodal analysis, but on this part, I'm using the so-called current division theorem. So to know current division theorem, you may click the link below to watch my video about current division theorem. Now it shows that the current that passes through the 2 ohm resistor is equal to 260.8691 milliamp. So there you go. We have the same value that we have computed using Thevenin's theorem. So Norton's theorem and Thevenin's theorem are almost the same. These two theorems simplifies complicated circuit. The only difference between the two is that the Thevenin's theorem will have an equivalent circuit, a combination of a voltage source in series with a resistance, while the Norton's is a combination of a current source in parallel with a resistance. So how about if you have two different sources? So that is now be explained in example number 2. We're going to find the Norton's equivalent of the network at 1 kilo ohm resistor. So therefore, the 1 kilo ohm resistor is the load circuit. So here's the circuit we're in. As you can see, there is two sources. One is a voltage source and the other is the current source. So the first is to divide the circuit into two groups, a complex network, as what you can see on the line on square, or in what you call this, a dash square, that is the complicated circuit or the complex circuit, and the 1 kilo ohm is the load circuit. Therefore, removing the complex circuit will lead us to an open circuit where the 1 kilo ohm has been removed. So the next procedure is to make a short circuit on the load part, or on the open circuit portion. So in this way, we will get the current at that portion. So using nodal analysis, so for those who have not or don't know how to use nodal, you may view my video about nodal analysis. So in the nodal analysis, we have 3 nodes. Then the last node, the third node, will become our reference node. Therefore, the node 1, which is connected to a voltage source, it has a value of the voltage source itself, because the voltage source is also connected to the reference node. Therefore, the voltage at node 1 is equal to the value of the voltage source, which is the 4 volt. So now we're going to compute the voltage at node 2. So remember, tail minus head. So the current is flowing out. So therefore, the equation will become V2 minus V1 over 2K, or 2 kilo ohm, plus V2 minus V reference over 3K minus 2 milliamps, since the current 2 milliamp is entering the node, and equal to 0. So simplifying the circuit and substitute the values of V1 and the V reference will lead us that V2 is equal to 12 over 2.5, or the voltage at node 2 is equal to 4.8 volt. So therefore, if we had a 4.8 volt, so to get the current SC, or the current that flows through the short circuit portion on this portion, it is the current that passes through the 3 kilo ohm. So using Ohm's law, so V over R, so 4.8 over 3K. So which is equal to, so the current, short circuit current, is equal to 1.6 milliamp. Now we're going to compute the Norton's equivalent resistance seen at the open circuit portion, as seen on this portion. So by killing the sources, since we have a voltage source, we're going to kill the voltage source and replace it with a short circuit, and killing the 2 milliamp, and we leave it as an open circuit. And it shows that the Norton's equivalent resistance is a series combination of the 2 kilo ohm and a 3 kilo ohm. Therefore, the Norton's equivalent resistance is equal to 5 kilo ohm. Now, combining the two, we will have now the Norton's equivalent circuit. We have the 1.6 milliamp as the value for the current source and 5 kilo ohm as the value of the Norton's resistance, in connected with a 1 kilo ohm, which is our load. So there you have it. We have simplified the complex circuit from a combination of a series parallel resistor into just a 3-component using Norton's theorem. Thank you for watching. I hope you understand my video, and if you like my video, kindly click like and share it with your friends so that your friends will understand how to use Norton's theorem. And please subscribe to my video and click the bell below so you will be notified if there's a new video that I will be posting. And don't forget to comment all my videos so that I will know what you want, or if you like my video. So see you next video. I'm going to do more of this video, and thank you. See ya.